All right, good evening, everyone. Thank you so much for joining in our fifth webinar. I'm so excited that it's already 5 webinars, and so thank you so much for showing interest. And I think last 2-3 we've been doing like every week, but still the enthusiasm is there. So thanks again for joining in. So before this has become like a ceremonial thing, that every time we get new IICOSE, new members or potential members, so we would like to start with very briefly, like 30-second introduction to IICOSE. So IICOSE is the largest professional not-for-profit society for advancing and promoting systems engineering and its practices. IICOSE has over 18,000 members all around the world. Has 53 technical working groups. Many of you I know are part of some of the technical working groups like architecture or model-based systems engineering, and like PHM working group, which is essentially organizing this webinar. So thanks to the PHM working group. And we have around 74 chapters and in 35 countries, and 3,700 certified professionals of IICOSE. IICOSE India, so IICOSE is completing 30 years. So IICOSE as such also has a milestone this year, and IICOSE India also is completing a milestone, which is completing 10 years of promoting systems and advancing and promoting systems engineering in India. We are a small group as opposed to be global, and we are around 160 individual members and around 61 certified professionals in India. And we have apart from, among the 53 technical working groups, we have 3 local technical working groups on architecture, MBSc, and PHM. On the left side of the screen was updated in the last webinar when we did the webinar, and we received recognition for this chapter. So for last 3 years, we've been receiving Silver Circle Award. That's an appreciation of the work done by the chapter for the members. But last year, we got awarded a Gold Circle Award, which is promotion, really excited. And then over and above that, we also received Director's Award for most improved performance of the chapter in 1 year. So yeah, really excited, and thank you for the entire team, and thank you for the members for always conveying what they want, and for the committee to be able to bring to you what you want to hear from this forum. With that, yeah, this is something that we've already posted and announced that we are completing and celebrating 10 years. We had grand plans in person, but I think this is becoming grander as we are doing our 5th webinar, and the next 4 are already lined up. So really excited. I hand over now to Partha and then Prasanna to talk about PHM Working Group and introduce our speaker for the day. So over to you, Partha.
Thank you, Stuti. Is it audible? I am audible?
Yes.
Yeah. Hi, good evening, everybody. Once again, welcome you all to this wonderful session. I would like to introduce India PHM Working Group, which was launched in December 2019. No doubt, prognostic health management, PHM, or predictive maintenance topic is very relevant across today's industry, particularly in Industry 4 era. PHM provides solution to reduce maintenance cost, enhance availability, reliability, and even safety. PHM provides integrated solution of present and future health assessment, planning of operation, maintenance, logistic in enterprise level. This is a multidisciplinary topic which embraces a wide range of enablers, starting from system engineering, sensor technology, advanced analytics, big data, operational research, and tool related to decision support. So PHM technology is evolving. Comprehensive regulatory standards are yet to be available in complete extent. Success of PHM system highly depends on the rigor of system engineering process. IICOSE, the leading promoter of best practices in engineering of complex systems across the industry. So IICOSE is an ideal platform for hosting the PHM working group. That's why INCOSE India chapter came up with idea of launching PHM working group in India. Key focus of PHM working group: contribute, review guidelines and technical products on PHM. Particularly, SAE has been already contributing a lot on different PHM aerospace recommended practices. This group will be a platform to work with SAE and contribute and disseminate knowledge, even to contribute those ARPs, and create opportunity and means to share best practices on PHM across industry. With this introduction, I like to express that we are very glad to have Dr. Ravi Rajamani as a speaker. He is very much eminent speaker on this very topic, PHM system engineering and standards. I'm sure this session will be very much exciting. I now hand over to Prasanna to introduce Ravi. So over to you, Prasanna. Thank you.
Yeah. Thanks, Partha. So, hello everyone. So, welcome all of you for this the first webinar organized by the PHM work group of INCOSE India. And so we are also privileged to have our mentor, Dr. Ravi Rajamani, as the first speaker of the first event being organized by this work group. So with that, so I would like to give a brief background about Dr. Ravi Rajamani. So Dr. Ravi Rajamani is a renowned name in the aerospace industry, especially in the PHM community across the globe. He is currently an independent consultant working on applying model-based and data analytics techniques to aerospace and other complex systems. In the past, so Ravi has worked at aerospace majors like Meggitt, United Technologies Corporation, and GE. And so he is also a very active member of professional bodies like SAE and the PHM Society. So he is a fellow member of SAE International and also the Institute of Mechanical Engineers. And so currently he's serving as a editor-in-chief of the SAE's International Aerospace Journal. And so his academic years were in premium institutes like IIT Delhi, IISc, University of Minnesota, and the University of Connecticut. And so Ravi has also authored several books, book chapters, journals, and conference papers, and he has several patents to his credit. So with this, I would like to welcome Dr. Ravi Rajamani. So Dr. Ravi.
Hey, thank you, Prasanna and Partha. I noticed, can you hear me?
Yes, Ravi.
Okay.
You're good.
I noticed that Partha didn't turn on his video, even though he asked me to do it. All right. What I'm going to do is try to get back the sharing. That went away with the... All right. Let me see how this works. We know it works. Share screen. Share. And let me know if it you can see my presentation.
Yes.
You can see the presentation?
Yes.
Okay. Good. And let's try that again. Swap. All right. Can you still see it?
Yes. Perfect.
All right. Okay. Very good. So I'm going to talk about prognostics, health management, systems engineering and standards, and also some certification issues related to PHM. That's, I think, very important, and hopefully at least those in the aerospace world will understand this probably a little better than the people in the automotive or other sectors. But yeah, just ask me questions if you don't get what I'm talking about. Okay, Prasanna did a good job telling you what I am, so I'll skip over this. There'll be three main topics today: prognostics, health management. I'll give you a brief introduction. We'll talk about how systems engineering is very important for PHM, at least in my opinion, and then where the future of this is going. Okay, so what is prognostics and health management? I think Partha did a good job telling you what how it is beneficial to, at least in the aerospace world. What we believe it is, if you look at the diagram at the bottom right, what we think, what we state, it is an end-to-end capability. In other words, that uses sensors to collect data. It uses analytics to figure out what that data means. And ultimately, it actually comes up with some actions based on that analytics. So it's an end-to-end process that starts from the data, actually starts from the sensors and ends in the action. What is diagnostics? Diagnostics is the determining, looking at all the information that you have on hand, determining the current health condition. It's a very causal process. Prognostics is an anti-causal process. It is predicting the future based on what you have information up till now. So diagnostics is the assessment of the current condition. Prognostics is the prediction of the future condition. And obviously that has to be based not just on the information that is we have at present, but also on the future estimate of the operations of the system. So that's the key, which means along with it comes uncertainty. So prognostics and uncertainty go in hand. Health management is taking all this information and actually figuring out what to do for maintenance of that system. We look at it in architecturally in this 5 steps: sense, acquire, transfer, analyze, and act or display. So it's, the acronym is SATA. It's a little different from the OSA CBM architecture, which a lot of you are probably familiar with, and I will tell you how they line up later. And PHM systems manage assets, and Partha mentioned this very succinctly. You have to deliver guaranteed performance. You cannot compromise on that. And you do that, and PHM increases your availability and lowers life cycle costs. But the entire idea, at least in the aerospace world, and obviously in other worlds as well, is never to compromise system safety. The whole certification around aerospace is how to ensure safety. And nothing that we do should compromise that. If anything, it should enhance that. As you all know, aerospace infrastructure, the ecosystem is very complex. You have not just the flying asset, but you also have an entire infrastructure and enterprise that backs it up. So the SATA model lies within this bigger system that actually supplies parts, supplies information, etc. Analyzes information. There's the logistics that are associated with it. There are engineering associated with, etc., etc. So there are several pieces of this, as I mentioned. There's the onboard piece. There is the transfer piece, and that's becoming more and more important these days, especially with cybersecurity and other things that are influencing not just the aerospace sector, but the entire mobility sector. There is the offboard piece, where the transitional information gets downloaded, and then you do things on the ground. And then based on the actions, there is this entire enterprise level, the functions associated with the enterprise. What are some of the problems with the current PHM system? It's not typically part of the normal engineering design process. It's part of after the fact to correct the problems. I know you all, a lot of you have experienced this, especially if you're in this field. And therefore, because of this, there's no systematic development effort upfront. A lot of it is after the fact. Budgets always get cut when the larger program runs out of funds. The ROI on this takes much longer than for a normal aircraft. An aircraft takes a long time anyway to make money, an aircraft program, but the PHM systems takes even longer. And while this is no longer that true, there aren't people who are actually trained in the discipline of PHM. That's changing, but not fast enough, I think. And systems are not health ready. In other words, they are not designed from the beginning to be installed in a PHM ecosystem. Well, part of the solution to this, obviously systems engineering is a big part of it, but also a dedicated team, protected budgets, shorter term off-ramps. In other words, you want wins that don't take 35 years to get realized. And again, I must emphasize that training is a big part of this. And standards is another thing which I've been involved in a lot, is also comes into making PHM a success. So how does the systems engineering part of it, you've seen this cartoon, I'm sure. Essentially, we all know, and since you are all members of NCOSI, you do know that systems engineering is a big part of it and is a big important part of any design process. That's no different for PHM. The costs obviously go up exponentially if you have to make changes in a program down the road. That is true of any major program. It's certainly true of programs that involve aerospace, for sure. And I don't know if there was a PhD thesis in Australia, I'm forgetting the name of the author, who actually did an analysis and figured out that if you spend about 15% of the budget in a program on systems engineering activities, the reduction in cost and schedule is fairly significant. So that's something that obviously you won't do it for a 2-week project, but a major project, if you fund it properly, you're going to get a better return on investment. Sorry. Okay. I'll give you, at least to motivate this, I'll give you an example of where the lack of a systematic approach to the design of PHM systems actually came back to bite an OEM. So there was a problem in a certain aircraft engine company's engines, where there was a problem with the fan blade retention. I won't go into details. And this diagram that I showed, this is nothing to do with this particular engine. So don't try to infer which engine this was. So there was a retention problem of the fan blade, and one of the issues was that it would come loose, and they realized that they had a vibration system in place that would give very clear indication of the fan blade coming loose early if you analyze the system. So you could take the vibration information, you could download it, analyze it, and trend it, and it was very clear that you could pick up this problem. However, the FAA would not allow that EHM system to be used because it was not designed in a systematic manner. What does that mean? It was slapped on after the fact. So the key that take away from this, so what did the OEM have to do? They had to actually institute inspections, regular inspections that are millions of dollars of extra cost, where they could have easily taken care of it using an EHM system had it been designed along with the engine at the beginning and certified. So having a systematic, system-based, system engineering-based approach to a design of PHM system is the key. A lot of you, I'm sure, are aware of the ARP 4754 process, which is sort of the systematic systems engineering approach that has been translated to the aircraft certification world. And what we are trying to do within the PHM discipline is try to adapt our systems to this overall process. There are certain keys differences between the two, and one of them is very obvious, is that the ARP 4754 process is only for airborne systems, whereas what we design is very much an end-to-end process that involves onboard components as well as off-board components. So we have to adapt the system to our discipline and our programs, but we have to do it within the context of this kind of a systems engineering process. So one of the applications of systems engineering to PHM, like I said, is obviously, Partha mentioned this a little in the beginning, the cost benefit analysis. This is a key, every program that I've been involved in. And in fact, I don't know, some of you may be part of UTC, or now I guess Raytheon. A major program that happened when I was at Pratt & Whitney was the geared turbofan. And I'm quite proud to say that using fairly validated cost benefit analysis, we managed to get EHM, engine health management, into the geared turbofan from the very beginning. So that's a extremely important part of this. People don't believe that PHM makes you any money, so you have to be really careful about this. Obviously, the rest of it you know very well. Requirements management, architected definitions. I'll go through some of the examples of that relate to PHM. Model-based design, that's a huge part of PHM these days. Almost everything we do today is model-based. And in fact, associated with that is model-based analytical VNV as well, validation, verification. And the key to this PHM is really how it integrates with the MRO, maintenance, repair, and overhaul business. That is the key. That's the only place you can make money with this. So I'll talk to you a little about where we are going with this in the future and near future, actually. Requirements. This is interesting. You all know that requirements flow down from the higher level objectives, right? That's what we've all been taught within our systems engineering discipline. In this case, this has been pulled straight from the JSF, Joint Strike Fighter requirements document, or rather this is not a requirements document. This is the very high level needs statement. Affordability, redundancy, and keeping the same level of safety. I don't know if you know what the JSF is. The Joint Strike Fighter is the 5th generative fighter replacement for a twin engine fighter, which is sort of the F-22. So the F-35 was a single engine, and the requirement was that it would be keeping the same, it would maintain the same level of safety as something with 2 engines, which is huge. So having a single engine aircraft with so the PHM system was a basic requirement for obtaining the same level of safety as the F-22. So that's how you derive requirements from higher level needs statements that at the face of it, you don't realize. If given this, you really don't see where the PHM comes in. But thanks to some leadership within the NAVAIR, a lot of PHM functions came about from the JSF because of this needs. So that's how this is just an example of how the requirements get derived from the needs statement. I talked about the OSA CBM model, which is on the left, and the SATA model, which I described. So you have the sense, acquire, transfer, analyze, and act. I don't know if you know what the OSA CBM model is. Obviously, CBM is condition-based maintenance. Open source architecture's condition-based maintenance architectural model. This is by the Mimosa that was started by US Navy along with, I think, Collins or Hamilton Sundstrand was a big part of that. Nobody knows what Hamilton Sundstrand is anymore. Anyway, so they have this 6-level model, which is the DA, DM, SD, state detection, health assessment, prognostics assessment, and advisory generation, which lines up pretty much with, well, it doesn't quite line up with our 5-state model, but you can see some parallels between the two. This is an architecture of the PHM system that we use pretty much on all our documents. The documents that Partha was talking about within the ARPs that the SAE aerospace sector has been developing. I talked a lot about the model-based design. Gas path analysis is a key part of engine health management. I talked to you about the gear turbofan. This is a key component of that. So what a model-based design system for an engine health management consists of is, if you have these, you have identified these physical problems like erosion, corrosion, fouling, etc. If you look at it, what happens because of that, it results in a degraded component performance. And the way we assign those performances in the gas turbine is essentially by 2 major factors. One is efficiencies and flow capacities, which essentially means that it's the area of the flow within the turbine. And what that does, the degraded component performance does, is produce some changes in measurable parameters. This is what you're sensing. So everything we do within diagnostics or PHM is an inverse problem. So taking the measured parameters and analyzing it using model-based means allows us to estimate the degraded performance characteristics. And from that, and from the signatures associated with that, you can actually do the correction to the problem. You can identify and correct the problems. And this is the folks, a lot of work has been done by NASA, Glenn Research Center, GRC, and Don Simon is one of the leading players in this area. I wouldn't bore you with VNV. I think that's important. The only thing I would say is model-based validation of requirements is becoming a big deal. You don't, because in the PHM world, the validation becomes very difficult. You will have to sometimes, if I tell you that I will save you 20% in your life cycle costs, you're not going to wait 30 years to realize that. You have to do it with a model-based design or model-based simulation or some means of doing it analytically. That's the key. That's the only thing I want to comment here. And then I think what is important for us is to see what the future of this is. Systems are becoming more complex, clearly. And as you all know, systems engineering is an absolutely essential part of developing a complex system. PHM, by its very nature, is interdisciplinary. It cuts across all the disciplines within, well, in our case, aerospace engineering, but it's the same thing for mobility, automobile, or any other, even manufacturing. A lathe has interdisciplinary, maybe not as complex as an aerospace system, but it certainly has electrical, mechanical, and chemical parts of it that have to be taken into consideration. And past experience will be key to sustaining PHM in the future. In other words, how things have worked in the past will have to be used to validate the future, especially when it comes to cost-benefit analysis. So what I would like to do is to conclude with my vision of where this is going. And I think I've got about 10 minutes, and that would be, I think I can finish that in 10 minutes, or maybe even less. And then we'll open it up for questions. So here's so maintenance, repair, and overhaul is kind of where PHM really resides. Why do I say that? Even though it has all aspects of engineering associated with it, it really makes money when you apply it to MRO. It's in the maintenance area that all these analysis, all the algorithms, everything that we do ultimately results in maintenance. So it is important to look at the maintenance part of it and then work backwards. So in the aerospace world, in the commercial aerospace world, in the 60s, when the 747 was coming on board, what was called what is now called the Airlines for America group set up the maintenance steering group, MSG, to develop systematic maintenance practices based on what is known as reliability centered maintenance. So there were 3 versions of MSG. They were called MSG 1, 2, and 3. These were the guidance based on reliability centered maintenance, especially for doing maintenance for the 747. And that has evolved over the years. And every 3 years, there's an update on the MSG guidance. And the only reason I mention that is we believe that PHM, any maintenance related to PHM will have to come in through that MSG process. So briefly, in the past, in the 40s and 50s, most of the thing was hard time. In other words, you fly a certain amount, you do inspections and maintenance. And some amount of on condition maintenance was there. With the MSG 1, 2, and 3, we started getting in more into the reliability centered maintenance and more into soft time. In other words, things based on condition. On the technology side, in the late 70s, we got ACARS. ACARS is a way of actually getting data off the aircraft. So you could get real-time data, and that allowed you to do more maintenance, more analysis on the fly. At the same time, SAE set up E32, which is the Engine or Propulsion Health Management Committee. This was in 1975, and to develop standards related to engine health management technology. So this was the SAE Technical Committee that was set up. And on the software side, DO 178 and DO 178A, B, and also the 4754 that I talked about. So these all came about in the 80s and the 90s. And from a engine health management point of view, with the ACARS came extended gas path analysis, which took information from not just the basic parameter, but extended parameters. So which meant that in the engine, at least the one that I'm more familiar with, extended gas path analysis came into being. There was interstage pressures. There was not just the N1, N2, and EPA. There were more than that. Okay, so in terms of certification, HUMS, which is Health and Usage Management System for helicopters, there was some certification of that in early 90s, and performance-based logistics, which is a Department of Defense program in the US, came about in the late 90s, and early 2000. You had the Department of Defense CBM Plus program. So a lot of these milestones happened before we even got into the 2000s. This century, one of the major developments within SAE was the establishment of G11 SHM, which is Structural Health Management Program. And that is developing a lot of standards related to structural health management. And what is going to happen in the future? More electric aircraft. There's a huge, what is now called sort of the fourth revolution in aerospace, which is the electric aircraft, autonomy, urban air mobility. All of these things are coming about. So we're going to see a huge development through the 20s and into the 30s. I know that we've had a bit of a downturn thanks to this COVID crisis, but I don't think that that will last. I think it will pick up. It'll be a little slower, but we will get to a certified Part 25, which is a transport big aircraft, by maybe the end of the 30s. That's at least my prediction. We already have a certified small Part 23 certified electric aircraft today in 1920, so it shouldn't take that long to get to Part 25. In the SAE side, a lot of work was done at the beginning of this, in 2011 on establishing IVHM steering group, and which, by the way, now I'm the chairman of, just starting, and the HM1, which is the IVHM technical committee. I think some of you are working on some documents. I know Partha and Prasanna are related to HM1, so that's fantastic. I need more people from the Indian aerospace community to join this. Ravi Kumar from Infosys has been doing a lot of work, and it will be great if more people do join in. The electric aircraft steering group came about in the last decade. Digital and data steering group, G31, G34. G31 is electronic transactions in aerospace. Ravi Kumar actually is the vice chair of that group. And one of a very exciting new development within aerospace is G34, which is the technical committee that is working on AI in aerospace, so artificial intelligence in aerospace. That's pretty exciting new development. So I'm happy to be part of that, and I'm sure you're going to hear a lot more about that. And Cranfield University has been doing a lot in this area. They set up the IVHM Center in 2009, I think it was. And now they're setting up the Digital Aviation Technology Center there to work on digital issues related to aerospace, which is, I think, the future for us. One of the things that how do you get PHM into the MRO, the maintenance infrastructure? You do it through what are known as maintenance credits. So if you look at what the definition of the maintenance credits is within the aerospace context, it is approving a new or modifying an existing maintenance procedure using well, IVHM or PHM technology in such a way as to save costs without compromising continued airworthiness. It's not earth-shattering what we are trying to say here. Essentially, what we are saying is you look at a existing maintenance procedure, and by the use of IVHM or PHM technology, if you can change it, say you lengthen the inspection interval, or you eliminate a specific procedure so that you save costs without in any way compromising airworthiness, that's essentially earning maintenance credits for your procedure. And that's how we, I believe, we go about getting PHM into the aerospace world officially. There are certain things that are already earning maintenance credits, like vibration monitoring, takeoff EGT margin. EGT is exhaust gas temperature margin monitoring, which is related to ETOPS, which is single engine operation. I'm sorry, twin engine operation. Oil debris monitoring, and a few rotorcraft safety critical parts like main hub rotor, and also the gearbox are under certain limited maintenance credits programs, not all though. SHM, the AISc SHM group that I was talking about, is doing a lot in this area, and they're working with the MSG group to do it. In the future, brakes and tires, batteries, APUs, landing gear components, all of them will be attacked or addressed through the maintenance credits procedure. I think that's the key to getting PHM to make a difference in the MRO world. This is kind of the process for getting this into the MRO world, and I'll give you a very brief overview of what happens. The maintenance review board, which compose of authorities, FAA, EASA, DGCA, etc., operators and OEM, they get together and figure out how a maintenance program is essentially established. That goes into the maintenance review board report, which starts the maintenance plan, which then goes to the OEM that develops the maintenance planning document. And then they hand that over along with the aircraft, with the asset, to the operators, who then come up with the detailed maintenance manuals, which is a big document that actually tells you which bolt to go unscrew to actually get to the problem. And then once problems are found during the operations, that goes back and modifies this. So that's how you get engineering changes, etc. That gets, so this loop is complete. And then there is this International Maintenance Review Board Policy Board, which keeps looking at this process and develops procedures for the rest of the world. Now, DGCA is not part of this yet. I don't know why. However, they do take guidance from them down the road. So I'm hoping that India becomes part of this, right, of this process in the future. There is a document that I authored recently, which just came out a couple of months back, Unsettled Issues Concerning Integrated Vehicle Health Management, IVHM Systems and Maintenance Credits, which lays out some of the issues associated with obtaining maintenance credits for PHM systems. And I don't know if you'll recognize some of these people, but they helped me with this document. I think that's really all I have to say today. I talked to you about systems engineering being critical to a multidisciplinary process such as PHM. About 15% of the budget, if it goes into this for a big project, really brings dividends. Certainly the Defense Department within the US, and I'm sure that is true of India as well, will not undertake a major program within systems engineering. Well established. Standards are extremely critical, and I know some of you know that. And to conclude, I would say that the only way to get to PHM to make a difference is through this maintenance credits process. That's the clear way of doing it, and we are working towards that. And certainly, if you guys are interested, just let me know and we will include you in the process. Thank you. I guess I'm open to questions.
Thanks. Thanks, Ravi. Those 45 minutes were really valuable to most of us.
Hey, it was less than that. There was 5 minutes somebody else spoke. It was exactly 40 minutes.
Sorry for that error, plus or minus.
Yeah, okay.
So we have a lot of questions already flown in.
Okay, sure.
So we will try to cover as many as possible within the time available. So the first question is, what are the enabling disciplines other than systems engineering that are must for one to develop in this PHM field?
So for me, I think really it's modeling. That I mean, I believe that fundamental mechanical engineering, electrical engineering. Why do I say electrical? Because these days electronic components. If you can model an IGBT, that's a fantastic thing. If you can, other than modeling a gas path for a gas turbine. So I think fundamental engineering, aerospace engineering is a key part on the aerospace side. For manufacturing, there are other systems. I mean, you cannot get around fundamental engineering. I think we lack that. We jump into software all the time. Clearly, software is important, don't get me wrong. But I think fundamental engineering is more important than anything else.
Okay. So the next question is, what is the progress of PHM in automobile as per your experience?
A good question. The OBD system, the onboard diagnostic system, number 2 now, I guess, version 2, is something that has, it was actually instituted for emissions monitoring. But because it allowed you to put in algorithms, it allowed you to put in monitors, it allowed you to have a communication to the outside world, it became somewhat means of doing prognostics. GM and others, through the OnStar process, which is a satellite link, have managed to put more diagnostics into their cars. So we have seen some battery management for electric cars. We have seen clearly Tesla and other companies have done a lot with prognostics. But in terms of hardcore PHM, I think aerospace industry is far ahead in terms of analytics. The good thing about automobiles is it's not as safety critical, so the chances of getting implementing PHM on automobiles is a little easier. So I don't know what's going to happen in the future. I think it's going to probably overtake aerospace in terms of the kind of smarts that you put into it. So yeah, it's an interesting world, that's for sure.
Yeah. So the next question is on the legacy aircraft systems. So where exactly the health analysis is performed? Is it on-board or off-board or both?
On legacy, it's mostly off-board. For example, on the PW4000, Pratt & Whitney 4000, the GE CF6, all that, very little is done on board. All the data is captured off board and it runs on databases that are on the ground. In the future, the 787 has a lot more going on board, and I'm sure in the future a lot more will go on the onboard side. On the military side, it's just the opposite. Forget about the legacy in the military. The JSF has a lot of onboard algorithms. In fact, most of its because the fact that will not be in touch with the ground, almost all of the JSF's PHM algorithms are on board. But that's not true of commercial.
Right. So you mean they were designed for PHM? All
They
those
are
systems.
very much. I mean, that JSF is a great example. I don't think you're going to get another JSF for 20 years because somehow they broke the bank on that one. I don't know of any other. Well, actually, I take that back. The Eurofighter has a lot of fairly advanced systems, but somehow in the Eurofighter, some of the most advanced systems are off board, not on board. For example, usage-based lifing for the engine on the Eurofighter is an off-board system, not an on-board system.
Right. Yeah, on the similar lines, so I have another question.
Mm-hmm.
So what is the current trend in the retrofit PHM systems? Means I understand the design for PHM.
Right. A lot of it is, there are a couple of companies that make boxes that can be retrofit, that look at the bus. Altair is one that PwC, Pratt & Whitney Canada owns. They have a box that they made, which now has been converted to something called the eFast box, which goes on the gear turbofan, attached to the gear turbofan, which looks at data. And then I can do some analytics on board, or actually uses the satellite or the Wi-Fi or cell modem to get the information off. On rotorcraft, helicopters, a lot more work is done in retrofitting. There are small companies, actually, there are small and big companies that put vibration monitoring systems on retrofitting it on helicopters. On fixed wing, it's not as much, partly because it's more difficult to get an STC, supplemental type certificate, for systems to put on on a fixed wing. Helicopters, you're only carrying 1 or 2 people, so the safety considerations are probably not that strong as for an aircraft that's carrying 200 people.
Right. But I believe for the commercial aircraft, definitely this will be an expensive affair, right?
It's very expensive. People don't take it, mostly because of the certification regulations. However, like I said, if you can figure out if existing data, if you can do some analysis on the ground and come up with some maintenance credits that you can obtain, earn, it's easier, much easier to convince the FAA or any other agency that it is worth doing. It'll still cost money, but you can do it. In fact, Delta is doing it with something called CVM, comparative vacuum monitoring, and they're doing that on their 737s. Interestingly, Delta is doing it for a Boeing aircraft. So, and they're trying to get, they've been doing it for, in fact, the person you're dealing with, David Petrosky at Delta, he's the leader on that. You should ask him about it, the CVM. Okay. In fact, I write about the CVM in my book as well. So,
sure.
Yeah, that's something that Delta is doing for getting an STC for that.
Sure, thanks. So now I'll move back to a few more questions from the audience. Yes. I think I have taken too much time for myself.
That's the prerogative of the chairman.
So next question is how PHM can be adapted for healthcare systems?
Oh, that's interesting. There is, within the PHM Society, there is something on monitoring the human being. I suppose you could use a lot of the model-based algorithms, the AI and the ML stuff that we are developing. You can do that for human beings. But I think they're probably ahead of us there. IBM Watson, you've heard of, and it does a lot of analysis using AI. So I don't know, maybe we should learn from them. Our problem has always been certification. So no, they are up there. They are doing very well, in fact.
Okay. So I think the next question is on the similar lines. What could be the possible reduction in the maintenance costs if we go with AI and ML?
So AI ML is, I mean, it's still infancy. There's very little. Ultimately, the fundamental AI ML is non-deterministic software. In other words, it's for the same inputs, you'll get a different result down the road. The question is, how do you structure that into a certified process? I mean, if you don't have determinism, you're not going to have an easy path to certification. Once you figure that out, then I think you can make, I mean, even with normal PHM, you can get 15% reduction in 15 to 20%, 25% reduction in costs. With AI, you can probably double that. You never know. But it'll take a lot more work. And I think that's what we are starting to do with the technical committees like G34, etc.
Right. Moving on to the next question, how the PHM and IVHM are related with respect to aircraft? So is
the way
PHM...
I think of it is PHM is a discipline, prognostic self-management. It's like control system. IVHM is a specific vehicle integrated health management system. So when you have an integrated vehicle health management system, that's a instantiation of PHM. PHM is a discipline. IVHM is a instance of that used at the vehicle level. And then you have component level PHM systems as well. I mean, if you have a vibration monitoring system that deals only with, let's say, bearings, that's a component or an equipment health management system. When that goes up to the vehicle level, then it becomes an integrated vehicle health management system.
Okay. Yeah, next one. So what role does digital twins play in PHM?
So everything I've said is a digital twin. I mean, a model is a digital twin. So yeah. We've been doing that since the 70s. We've been developing digital twins for aircraft engines since the 1970s. So that's the only thing now is that it is becoming far more complex. So you have detailed finite element models that you're using as a representation of the real thing. But low order models for components we've been doing since many years. So we know how to use digital twins. We in the PHM community have used digital twins. In fact, we cannot do our job without digital twins, and we've been doing it.
Right. So we are left with just two more questions.
Wonderful.
I think we can quickly. So given that electric vehicle and electric aircraft are the future of mobility, what is the future of battery PHM?
Battery PHM is very mature, I think. Well, not mature, but it's very strong. There's a lot of work going on in battery PHM, and the thing with lithium ion batteries is you definitely need PHM to make it work, because you need to have extremely good state of charge and state of health estimates and remaining useful life estimates. So it's definitely something worth studying. So if anybody has interest in battery PHM, it's a good field to be in.
Yeah. Yes. So now we are in the last. So what is the extent of implementation of AI and ML in modern 5th generation fighters IVHM systems?
I mean, I'm going to say 0.
Okay.
So nothing. I mean, maybe they have some threat identification or something on ground-based systems, but on board, I don't know of any. I mean, I certainly don't know all the secrets of all the air forces. So as far as I know, there's no AI ML.
Right. Sorry, actually another question popped up in the last minute.
Okay.
Maybe we can close with that. Are aircraft manufacturers pushing more for federated architecture for aviation or central and IMA architecture? Which works best?
That's a good, very good question, actually. So good way of. There's been a lot of debate on how to do it and now the problem is with it depends on two things: security and bandwidth. If you have the old kind of data where you get one shot per flight, then bandwidth is not an issue. So having a centralized system works just fine, and it's right. That's what we've been doing for years and years and years, because you don't have that much data going back and forth. However, in the future, with a lot more concentrated high frequency data that is needed for analysis, you cannot be sending that all over the place. So having different distributed analysis centers would be the key, but you have to then have some kind of an integration between these federated analytical centers, so to speak. So I think we are getting to that. We're getting to a distributed architecture for analysis. What it will look like, I don't know.
Okay.
We have been centralized for now. Definitely,
right.
Very much centralized.
Right. Yeah, thanks, Ravi. So that's all we had from the Q&A. And I think it was a wonderful session.
Oh, thank you. I hope somebody got something. I hope you all get inspired to start working in this area.
Thank you, Ravi. I think this is a very energy-packed and very enriching session. As you can see, the number of questions that just kept coming in. Thanks a lot for your time. In the end, you did mention that how people can join you towards this work. So if you can let us know, I think a few people.
Yeah. Talk to Prasanna and Partha.
Sure.
They are supposed to be working with the SAE now.
Sure. Sure. So we'll.
And I think one of the things that we have taken on is systems engineering as part of PHM development. So you guys know more about it than all of us. So we can certainly use your help.
Great. Okay. Yeah. Thanks a lot for that, and we'll redirect all the interest to Prasanna and Partha so they can lead the way with that. Yeah. Thank you again from the entire chapter committee for your time and for such an enriching session. Have a great day.
Sorry, ma. No, Rona. All right. I'm going to sign off now.
Yeah.
Thank you. Thank you,
Bye
Ravi.
bye.
Yeah, bye.
Thanks, Prasanna. Thanks, Partha.
Thanks.
Yeah, bye.
Thanks.
Oh, yeah, we can see Partha finally.
Hello.
He has a helper as well.